Good morning. Okay, so we'll finish the reviews on probability and statistics. Okay, and then we'll go into the Kalman filter design. Okay. So in previous lecture, the review was finished until covariance matrix, right? Okay, so then let's keep going along that line there. So the next one here, using that numbering, I think we're at the 7 now. So here, let's look at the random vectors. Okay, look at random vectors. So previously, basically, we look at the individual random variables, right? So random vectors, basically, if you consider two variables, x and y, and they are vectors, and each vector, okay, contains, let's say, okay, n number of random variables. So it's a vector contains n number of random variables. Okay. And same thing for y. You can have an n number of random variables. So xi's or yi's, so they are random variables. Okay. Yeah. And we just like before, we have expected value, okay, for this random vector. Okay. And it's equivalent to say it's the expected value of x1, x2, and xn. Okay. So same thing for the random vector y. Okay. Yeah. So and then we have, before this one, if it's a single random variable, we have the concept of variance, we have the concept of covariance, and we also have concept of correlation. So now we have, okay, a random vector. So we have this concept now, it's called cross correlation. Okay, it's the cross correlation between x vector and the y vector. And the definition or the formula for this cross correlation is, okay, so Rxy vector is equal to the expected value of x and y. Okay, yeah. So because this is x, this should be y transpose here. So basically, it's this vector times the transpose of this vector here. Okay, so this is n by 1. That's 1 by n after transpose. So you end up with n by n matrix set here, right? Yeah, and that's basically what that gave to us is expected value x1 y1 and up to expected value xn. x1 yn, okay, expected value xn y1, expected value xn yn. Okay, so that's the correlation, cross correlation. So you have a vector containing n number of random variables, right? Given this matrix that here, we have the cross correlation because you look at each one of the elements, they are essentially the correlation, right, for all the possible combinations between the two random variables. And covariance of this x and y. Okay, so you have two random variables. Then the covariance of the two random variables. So basically, we still use COV for covariance here instead of x and y. Single random variable is the random vectors. Okay. So definition-wise, this is still the same thing. So this is expected value x vector minus its mu. Now, the mu at here is not going to be just a single mean because it's a vector, right? So it's say this is basically mu x at here. So that's another vector here, huh? Yeah, and then time y minus mu y transpose like this. Okay, so this is the covariance for x and y. If you expand these things out, okay, basically we get another matrix. Okay, and another matrix here. So this matrix expected value x1 minus mu x1, y1 minus mu y1. Okay, expected value xy minus mu x1, yn minus mu yn. That's the first row. So you have basically the rest of the there, xn minus mu xn, y1 minus mu y1. Okay, so this is the covariance. Now this has become a covariance matrix now. Okay, it's covariance matrix. So when you have just two single random variables, what you have is just a single scalar quantity covariance. So this is actually more precisely it's called covariance, okay, matrix. Okay, it's a covariance matrix. This matrix can also be written as a similar format. You can write it as the expected value of x y transpose minus mu x. So expected value for the x vector, expected value of the y vector. So this is more compact basically. Huh? Yeah. Okay. Yeah. Okay. So the next thing is let's look at special case. If I change the y, okay, to x, so basically I'm looking at the covariance, okay, matrix, you know, for the x vector itself. So then what do we get then? So basically now we got this one is called cross correlation. If I change this y to x, it's basically called what? Autocorrelation. That's right. Okay, so the autocorrelation, so instead of writing x, so just write rx here. Okay, so that gives us expected value x square, x1 square, expected value x1 xn, expected value xn x1, expected value xn square. Okay, that's autocorrelation at here. Okay. So if you look at the autocorrelation matrix, the difference now is it's actually what? It's a symmetric matrix, right? The symmetric matrix. So this is symmetric. Okay, yeah. And not only symmetric, it's actually also so-called positive semi-definite. Okay, positive semi-definite. So what does that mean? Basically, you can pick, if you pick an arbitrary vector z, let's say, and we can prove that this z transpose time this matrix, the autocorrelation matrix, and then times this. This is basically a quadratic form. And we can show that this is greater and equal to 0. So that's basically the definition of a positive semi-definite for a matrix. Okay, yeah. So it's symmetric and it's positive semi-definite. Okay, yeah. So same thing for covariance. Then we have this autocovariance here. So for autocovariance, you're looking at now is this covariance, right? Okay, about self now. Okay, it's a random vector x. So let's say we write it as Cx like that. Okay. So the matrix for the autocovariance matrix is this. So basically it's expected value x1 minus mu x1 square, and then expected value x1 minus mu x1 xn minus mu xn. Okay, and the same term like that, it's xn minus mu xn, x1 minus mu x1, and expected value of xn minus mu xn. Okay, yeah. So that's autocovariance. So if you examine this autocovariance matrix, apparently it's also a symmetric matrix. Okay, it's also a symmetric matrix. It's actually also positive semi-definite matrix. Okay, so symmetric, okay, and positive. So semi-definite. Okay, that's autocovariance. For the autocovariance, if I look at this matrix set here, look at the matrix for each element of the matrix here. So this element is actually basically what? The sigma, the variance of x1, right? That's the variance x1. So let's say I call it the sigma 1 square. And this one here, this is x1, this is xn. That's basically covariance, right? Between x1 and xn. Okay, so we can write it as, let's say, sigma 1n. So sigma n1 and sigma n square. Okay, yeah, so can you also write it like that. Okay, so this is the covariance here. So I'll use this one here later just for our random vectors. Okay, yeah, we'll make use of this result here. Just a few comments. Okay, if you look at this compared to this the correlation matrix and the covariance matrix. Okay, yeah. So first, let's see if this mu x and mu y, basically the expected value of the two random variables are 0. So there's the means are the 0. If the mean are 0, basically, if you recall that for this term here, for the arbitrary off-diagonal term, for the off-diagonal term, those are expected value xn, x1, let's say minus mu xn, mu x1, right? Yeah, like what I showed you here. This is the covariance. So if these two are 0, then your covariance matrix has only this term left, right? Has only this term left here. So then that's actually what? That's actually the same as your autocorrelation now. Okay? Yeah. So basically your Rxy is going to be the same as your covariance. Okay. So this is actually important because in our case, when we design our common filter next, we often consider is our noise. Okay, they all have a mean value of 0. Okay, the expected value of noise is 0. So it's basically Gaussian noise. Okay, yeah. And if x and y are independent, okay, if they're independent as before, just like single variables, then the covariance matrix is going to be 0. Okay, yeah. I mean the cross covariance matrix. Okay, yeah. If xi's, okay, between basically the random variables within the x vector, and they are independent. Okay, if xi's are independent, then the covariance matrix, the autocovariance matrix, this matrix here, the autocovariance matrix, or this matrix, and guess what? All the off diagonal will be 0, right? So you only have, okay, it's a diagonal matrix now. Okay, it's a diagonal matrix. Okay. And same thing. And then if we keep adding one more here, so if this guy is independent, and if mu, okay, x equal to 0, so we get this autocovariance. We get autocorrelation is the same as the autovariance. Okay, autocovariance matrix. Okay, yeah. So we're gonna in the future, when we write this matrix, we'll write the sigma x like that. Okay, sigma x like that. All right, yeah. There's a very common, there's a very useful property or theorem that we may not use it, but I might as well just write it here. Let's say if I have a relationship between the x and y is this. Okay, suppose the y is linearly dependent of the x, so they're dependent, right? Then, and we know the properties of the random x vector. We can show that the y, okay, basically has a mean value of a mu x, so bigger. Okay, so y has a mean value of this plus b, okay, and it has a variance of this one. Okay, yeah. So the writing of n at here essentially that means it has a mean of this and has a variance of that, right? Yeah, so normal distribution. So it's pretty useful in terms of the transformation, right? You know, when you have one, then how to transform to the other one there. Okay, just a little bit, maybe a simulation here to show you a better understanding of what covariance matrix means here. So let's say in the, I'll show you what I have here. Let's say you can examine the code after the class. So I'm going to create two random vectors, okay, or two random variables. Okay, so let's say the first variable is called, I call it S, the other one is R. So the way they create it is creating as a normal distributed random variable. So S, so this is how you can create this one here. You can use RANDN. Okay, RADN give you a uniform distribution. Okay, and then if you multiply that is the 3 plus 10. So what this means is basically you create a mean of 10 and standard deviation of 3, or variance of 9 for this variable S. Okay, so let's say for the R, I'm creating is a variance of 36 and a mean of 20. So this is basically S and R created here. Okay, so then once we created this one here, so the idea is what's the if we create the vector Z, let's say the Z is SR. Okay, so there are two random variables, right? Then we look at it. Okay, so what is the covariance of this Z at here? Okay, the covariance of Z. that good? Yeah. So you should what you would expect to be the matrix supposed to be what, sigma s square, and then sigma sr, sigma rs, and sigma r square, right? That's what we'd expect from this covariance matrix here. Okay. Yeah. So if you look at this matrix set here, the off diagonal, basically these two, right, indicates essentially the dependency of the two random variables, right? Yeah. If the two random variables are independent, then these two should be what? Should be 0, right? Should be 0. So, but the way we create this one here, we use basically normal distribution. So the S and R itself, they are supposed to be what? Actually supposed to be independent from each other. Okay? Yeah, they don't depend on each other. So giving a sufficient large number of samples, then we should have these two number, you know, because it's not an infinite number of samples, these two numbers should be close to 0, huh? Right? Yeah. So you can verify that, and we can see now, given the k equal to how much? 100,000, and this is what I get here. Okay? Yeah, that's what I get. Okay. Apparently this is close to 0, and this is 9, this is 36, right? That's what's supposed to be. Now if you plot this out here, okay, if you plot it out, you can see now this is basically this distribution, okay, of all the dots, okay. So apparently it's very clear, you know, based on this random variable here. So you see, okay, I'll bring it back to here. Ooh, some more there. Okay. Anyway, so if you look at this is x, here is the s, the random variable s, and the y direction is the random variable r. So if you look at the x-axis variation, that's about 6 we're talking about, and if you look at the y direction, that's about a 36, the variance that we're talking about here, right? Yeah. So this oval represent is a drawing 95% of confidence, basically to include all the points at here. Okay, it's an ellipse which has no inclination. So basically, it's this kind of ellipse, right? Yeah. So imagine if you have, let's say if you have a sigma, this covariance matrix. Let's say if you have a covariance matrix, let's see, x, okay, maybe is equal to 5, 4, 4, 6, for example. Okay, yeah, and this is not 0 here, right? It's not 0, and these two are positive, right? These two are positive here. So that the distribution of the two random variables is supposed to be looking like this. So basically, it's all centered. Okay, not centered. Just mostly will be within a ellipse, and that ellipse, okay, has, okay, a minor axis and a major axis, semi-major axis like that, right? Yeah. So I'm not sure if you've learned this or not. So this is the ellipse. You can create this ellipse set here. The basically the eigenvector of this matrix, there are two eigenvectors, right? I mean, yeah, there are two eigenvectors. So one of the eigenvector of this matrix represent what? Let's say maybe this direction, and the other eigenvector of that matrix represent this direction. So what's the significance of these two vectors or these two directions? Each direction represents a direction of the variance or dispersion of the data. So this vector here represents the direction that has the maximum dispersion of the data. Okay? Yeah. Okay.
So on your graph,
this graph?
No, the other one.
Yeah.
The small little guy.
This one.
That
Yeah.
It would be straight up and straight over.
Huh?
The eigenvectors?
Yeah.
Straight up.
That's right. Because of the diagonal matrix, right? Yeah. So when you have a diagonal matrix, one eigenvector, let's say maybe A0, the other one is 0b, right? Yeah. Okay. So the idea is basically the eigenvectors, right? Give you one direction. This direction is the less basically direction of a dispersion or variance of the data. Okay, or something I call the second most variance of the data here. The value, the eigenvalue of this matrix, right? The eigenvalue in the matrix represent is that they call what you call it, basically ellipse. It's called the major axis, the minor axis of the distance. Okay, so from here to here, from here to here. Okay, yeah. So when you it's useful basically when you draw this out, then you can clearly see, you know, which direction has more variance, which direction is less. If you have 3 variables, then you'll be able to draw an ellipsoid actually. Okay. Okay, so random vectors. Okay, so the next one here is a bigger topic, stochastic process. Okay, we're not going into too much details here, just sort of introduction. I know some of you learned a little bit in 460, but kind of student I don't think so. Essentially, the reason I bring this up is because when we're dealing with a common filter, here's our original system here. Okay. Okay. This is a clean system. Okay. This is a clean system here. But now what we do is we are going to consider a more general situation is this. So the system is not clean. It's being contaminated by noise. So this is called the process noise. Okay. And the process noise is basically a stochastic process, and that resulted in the whole system, the state equations at here is become a stochastic process. Okay, yeah. So that's why I wanted to bring up this question at here. All right, yeah. So what do I want to cover here is let's say we consider a stochastic process. So we use capital X of t to represent this stochastic process. Okay, yeah. So it's a random variable. Okay, it's basically a random variable. Okay. But it has a property not exactly like a typical random variable there. Okay. So what happens is this. It's not deterministic. So what does that mean is, if consider this is a random process, you give an initial condition to this. Okay. So let's say you give an initial condition right here. Okay, like this. Okay. So then you let the process basically evolve as time goes, right? So you will see that it probably goes, okay, like that. Okay, yeah. Now, because it's a stochastic process and it's not deterministic, so the next time, okay, if you assign the same initial condition, okay, same initial condition, and the response, okay, or the time history at here, okay, is not the same as, well, it's not going to go back. It's not the same as the first time anymore. Okay. Now, if you keep doing experiment, right? So every time you do it, you get a different response, basically. Is that good? Yeah. That's what we call it's a stochastic process. Okay. Yeah. So the number of experiments that you do, or the result that you obtain, okay, and often time we call that ensemble. Okay, but that's not reading here. Okay, yeah. So a very good example is basically, let's say you launch a space shuttle, and you're interested is in the temperature on the space shuttle, the external on the outside external when it coming back to Earth, right? So often in time, what you do is So I'm interested, okay, I use a T, I use S. So T represent at what time that you're interested, the temperature. And S represent is the number of the lunch. So you lunch the first time, the second time, and the 100th time, like that, right? Yeah. So you can, if you pick the same time, let's say, if you actually this is not the fictitious example. You can look it up on the internet. So let's say if you pick a time here. Okay, I'm not sure why they picked this time. So, and then you pick, let's say 175, 205, like this. So each time, right? So each time you get a different number. Let's say this is 207, and this is 209, right? Okay, Fahrenheit. Not Fahrenheit. Okay, Kelvin actually. Okay, yeah. Okay, so you get a different time. Basically, if I look at this one here, okay, so then what happens is if I choose a time t naught, okay, if I choose time t naught, if I go up, okay, and also go down for the other trial, okay, for the other trial. So every time, right, you get a different number here, okay, you get a different number, okay. So basically, for each instant, if you look at another instant and this instant, for each instant, it is a random variable. So basically, the x t naught, right, is a random variable. Okay, that makes sense. You pick one instant out of this stochastic process. That's a random variable. Okay, it's like our process here. Okay, our process. Okay, you ran it with the same initial condition. Okay, and if you pick one state variable and then pick one at certain instant k equal to 2 or 3, right? You basically get a random variables. Okay, they will vary around certain values. All right, yeah. So then the whole idea is now if this is a random variable and this is a random variable, so it doesn't matter where you pick, right? Then all the concepts that we have covered basically apply to the random variables that we were talking about here. So for example, if we can have a autocorrelation, let's say between not autocorrelation, correlation between this. So we write it as ET1 x T2, okay, like that, right? Yeah. So the writing or the concept that we have dealt with applies to all of this here. Okay. So covariance, okay, so I'm applying it for the moment t1 and a shifted t1 plus tau. So what do we have? We can have covariance x t1, okay, x t1 plus tau, right? It's the same thing. Okay, yeah. So that's stochastic process. And under the category, the whole umbrella, and there's one special one here, okay, it's called stationary stochastic process. Okay, stationary stochastic process. So what is a stationary stochastic process then? Basically, stationary stochastic process basically means doesn't matter which moment that you pick. Okay, doesn't matter which moment that you pick. You pick it here, you pick it here, you pick it here. Okay. The distribution, the probability distribution at each one of the moments that you pick arbitrary, they are all the same. Okay, they're all the same. So that's going to be the stationary stochastic process. So basically, distribution the same basically means, let's say, if I look at what is the mean, right, at the T1 and the T2, and they should be the same. And they all should share the same probability distribution function f of x, like that. Okay, yeah. So this is the probability distribution for the random, basically, right? For the random process is x at here. All right? Yeah. So that will basically become a stationary process here. Okay. Yeah. Similarly, then, if I look at the autocovariance of the function at here, so Cx, Cx, let's see, T1, I write as T1 plus tau. Okay, T1 plus tau. So we can let, because it's all the same, so basically you can let the T1 to be 0. Okay, look at T1 to be 0. Okay. And this writing can be just simply a tau. Okay, like that. Okay, so the Cx of a tau is equal to expected value x of a t minus its mean. Okay, x of a t plus tau minus the same, its mean is not going to change. Okay, if you expand this out, right, it's expected value x of t plus tau minus mu square. Okay, mu square. Yeah. So the key idea, essentially, you can just remember statistic properties, okay, of the process. Okay, they do not change, okay, with time. Okay, that's a stationary stochastic process. All right. Yeah. One example is when you're looking at the white noise. Okay, we'll explain what the white noise is. When you're looking at a white noise, the white noise is stationary. Okay, yeah. So if you generate the white noise, it's a Gaussian. Every time you generate, if it's ideal ones, okay, and the statistical property, it doesn't change. Okay, yeah. So number 9, let's look at the white noise. Okay. So we'll look at the discrete random sequence. Okay. Okay, we'll look at the discrete ones here. So discrete basically means let's say we're looking at is this W of n, okay, and n equal to, let's say, maybe 0, 1, 2, right, to certain numbers. Okay, yeah. Okay, so it's a discrete one, which means, basically the way you generate it, okay, you say, okay, it's at the W of n, the first time you generate, if you generate in the first trial, okay, you generate, I don't know, maybe 0.1, blah, 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 and then you trial number 2, okay, you generate another one here. So you can imagine, basically, if this is W0, W1, let's say this is 1, 2, and W2, right? So each one of them, if you look at this one, this why we call this is a stochastic process. Basically, each one of them at each instant, right? They are a random variable, basically. Okay, so W of n, W of 0, W1, and W of n, right? And they are, okay, random variables. Okay, they are random variables. So more specific speaking, they are called independent. Okay, let's see, we say independent identical distributed random variables. Okay, so like IID, distributed random variables. Have you learned this? Independent identically distributed, the concept. So anyway, it's not anymore. Okay. Okay. So let's see. all of them has the same statistical property. They all have a mean of 0, and they all have a variance of a sigma square. Is that okay? Yeah? Okay. So then the property of this white noise becomes this. So the property is first the mean, right? The mean of this white noise. Okay. We use W star bar. It's all 0. Okay. It's all 0. Okay. The autocorrelation, okay, or autocovariance, because this is independent identical. This is, let me write down, independent. Okay, identically, okay, distributed. Because they are independent, so W1 is dependent from W4, W4 is dependent from W100, right? So because they're independent, then the covariance, okay, or the correlation basically becomes the same thing. Okay, the autocorrelation matrix, right? In this particular case, it's a sigma square delta k. Okay, if you just compare between itself, so let's say this is W. This is basically expected value of a WK and WK, right? Yeah. Okay. Sorry, this writing in here. No, this is then it should be this. The writing in here. This is n plus k like this. Okay. So that's the correlation. Okay, the correlation between Wn and Wn plus k. So apparently, why I write this one here? This delta here is a, if you recall that in the Z transform, it's a Kronecker delta function, right? Kronecker delta. So that function basically means when k equal to 0, this is 1, right? It's a sigma square. If k is not 0, then this whole term is 0, right? Yeah. So if you look at this one here, when k is not 0, then these two, they are what? They're independent, right? Yeah. Then the correlation should be 0. Okay. If k is 0, then you're looking at this autocorrelation. So that's basically the variance now of itself. Okay. Yeah. Is that good? Yeah. So the white noise, okay, if you pass the white noise with a certain filter, okay, you pass this one here with a filter, okay, then what comes out this filter is not going to be a white noise anymore. This is basically become a color noise. Okay, let's call it Vn here. Okay. So, there's a simulation in my lecture notes. You can take a look at that. Okay. So it's basically a demonstration. Generate white noise, W here, and then look at its correlation. Okay. Basically, showing the spectrum here shows essentially, right, the same idea as what would expect it. Okay. Last part. So we have one white noise, and now the last part is really what we're going to deal with now. Now let's look at the white random vector, right? So I'll use a W out here now to indicate this white random vector. So this white random vector is W1k, W2k, and Wn of k. So this guy out here, okay, and k equal to 0, 1, it's basically the one that I just wrote it down if given a state space equation, that's the W we're talking about here. Okay, that's the W. Okay, that's the noise. Okay, and the noise has a noise for each one of the state variable, and the noise changes, right? Basically at a different k instant. Okay, yeah, that's a white random vector here. Okay, so if we write what's the expected of this white random vector, so we write it basically as W1 of k, Wn of k, and we're gonna consider them white, so we're gonna consider them basically the means are all gonna be 0. Okay, and for each one of the k, okay, for different key value, not just 1, not just 2, for any key value at each time instant, okay, the means all gonna be 0. If we look at the autocorrelation, right? So the autocorrelation for the W vector, okay, which is this guy here. We can write it down like that, and it turned out to be basically sigma W1 of k square and up to sigma Wn k square. Off diagonals all gonna be 0. Okay, all gonna 0 here. Okay. And because it's white and because it's independent, then the correlation, okay, autocorrelation is the same as the autocovariance. Okay. Okay. So these two generate the same matrix, which is this. All right. Yeah. Okay. So that's basically the reviews. I think I want to stop it here. All right. Yeah. Any questions? Yeah. There's a lot of things, background here, but just kind of jog your mind, and we'll make use of some of the things that we're written down at here. Okay. Yeah. All good? Okay. Not really. So let's move on to Kalman filter now. Okay, Kalman filter design. It's a filter, okay, and it's actually going to be basically an estimator. So let me write down basically the process first. All right. Yeah. So we're dealing with a linear system. So let's see. We're looking at is a linear model. Okay, state equation is this. Output equation originally is this, and now we have this one here. So basically, the idea of this here is the process. Okay, the process originally is the clean one. Then you have a noise, okay, goes into the process, and here's the output, and then you have the noise goes into the output. Okay, so this coming out here is the y of k here. Okay, so that's the idea. Okay, so we let's see, we have n by 1 vector here with a system order is n. Okay, this is n by n matrix, And let's see, we have let's see, R number of input to the system. Okay, then the H matrix is basically becomes N by R. Okay, if we have M number of output, then the C matrix is basically M by N. Okay, M by N. And WK and NK, they are noise. So WK, okay, the size needs to match with X. So this is N by K vector. Okay, and V of K, it's a noise contaminating the output. If output has M number of output, then this is M by 1. Okay, yeah. So if you write it out here, basically W of K then equal to W1 of K and up to Wn of K. Okay, and K is 1 and 2 and then up to N, capital N, and it keeps going. Yeah.
So this you're making your stochastic process, right?
We're not making it. This W and K is actually probably just naturally exists in the environment,
And then
right?
you can take this whole thing and throw it through a filter?
Oh, not yet. Just wait a second here. Yeah, not just put everything into a. There's a design here, right? Yeah. So just hold your horse. Yeah. Okay. Yeah. Technically speaking, yes, you put the signal into a filter. Yeah, which we call a Kalman filter. Yeah. Okay. So V at here, it's M number, so you can write it here V of K V1 up to Vm. Okay, yeah. So the idea is basically for W1 of 0, let's say, or W1 of 2, or W2 of 100. Okay, you pick a different one here. All of them, they'll work. They are all random variables. Okay, they're all random variables. And because of this, then the x1 of 0, if you look at this number 1 state at the instant 0, if you look at the number 2 state at instant, let's say 150, or if you look at the number 100 state, and there's no 100 states, yeah, it depends. So let's say 4 states, and then look at 10. So, and they are all random variables. Okay, they are all random variables. So things are a little bit different now, right? Yeah. So W of K and V of K, we're going to consider them as white Gaussian noise. Okay. Okay. So which means the expected value of these two is the same, 0. Okay, is the same 0. Because they are Gaussian white noise, so then these two, right, they should be independent. Then if I look at the correlation between these two, okay, if I look at the correlation between these two, that's not these two, W here. So first let's look at the W here. If I look at the autocorrelation between the W only, right? So what do we mean by W only? Let's say here your K value, your K value takes basically can be any values, can be 1, it can be 2, or can be 0, 2. Okay, can be any values here. So it's basically the same writing as we did. It's the RW. Right, it's the RW, the correlation matrix, which is what? Which is this, right? Which is this. Okay, yeah. You get essentially a diagonal matrix. It's actually positive definite because the elements on the diagonal matrix is all positive, right? It's all positive. Okay. Same thing for the V random vector. And you'll get RV. Okay, you get a RV. So these two are correlation, and because they're independent, right, among each other, So essentially, it's a correlation matrix. It's also the covariance matrix. Okay, it's the same because these two are the same at this stage. Okay, yeah. And W and V, between W and V, they are independent. So if you pick, okay, if you pick, I should have it transposed here because they are vector. If you pick a J for the W, if you pick a K for the for the V, J and a K could be different, and they're all 0 basically. Okay, they're all 0 here. Okay. And J here doesn't matter whether J equal to K or J not equal to K. Okay, doesn't matter. Okay, yeah. Okay. So typically what we write is we said, okay, W of K has a mean of 0 and has a covariance matrix RW. Or we write V, same thing, has a mean of 0, normal distribution, okay, and a variance of RV. Alright? Yeah. So maybe a vector here. Okay. Now, if we look at we look at the one of the state, let's see, what about the state? Let's say x at 0 here. Okay. I mean, this is a random variable. This is a random vector, right? Because it contains x1 of 0, x2 of 0, x3 of 0, xn of 0, and each one of them is random variable. So this is a random vector. And the random vector has a mean. Okay. If I look at the correlation here, okay, so sorry. So later we'll denote this one as a matrix P naught. Okay, a P naught here. So this is called, this P naught here is called covariance matrix for x initial condition, x of 0. Okay, x of 0 here. So P naught often in time, because of the noise, you can't predict where they are. So then the x of 0, the initial condition, they're going to change, right? So you will have to actually provide an initial value or initial matrix for as this P naught, okay, for our purpose to start basically the calculation or the computation. Okay, yeah. So what are we doing then, right? Here is a system. Okay, you have input, you have output. Okay, you have input and output. If the system is clean, right? If the system clean, as we learned in the previous case, so what do? We have an observer, right? We have the observer, and we take the input, we take the output, then observer spits out what? The estimates, right? The estimates. Okay? Yeah. Now it's the same thing basically. So now the system is not a clean system. It's contaminated by noise. But what we still want is, we still want to observe the state variables x of k. So we're going to still use this same structure here. We're going to take the input, we're going to take the output. Okay? Yeah. And then we're going to estimate this one here. Now the observer here is not going to be called just observer anymore. So if we do this, then for this one here, this is going to be replaced with the so-called Kalman filter. Okay. Is that good? Yeah. So Kalman filter, now you can get an idea. Is basically it's an observer or it's an estimator. Right? So what is estimating then? It's estimating your basically your x of k, right? So you're using this one here to come up with x hat of k for x of k. Okay, that's what basic common filter will do. Okay, now the whole objective of doing observation or doing estimation is basically you want your x hat of k, right? You want your x hat k to be the x of k, right? So basically you have an error, okay, due to this observation, okay, and that's what we learned, observation, right? Yeah. In a typical observer, what's the objective? You're trying to let the e to go to 0, right? Yeah. But now the thing is, you don't have a clean system. You have a noise contaminant system. So noise is not going to go away, right? So your E at here for a noise contaminant is for this stochastic system like this, okay? Like this one here. Your E, or your estimation error, it's not going to go to 0, definitely 0. So it doesn't matter what you do. You're not going to get exactly 0. Because why? See, if this is a stochastic signal, if this is a stochastic process, and this is going to be a stochastic process, then guess what? The E is a stochastic process, right? Yeah. So then, if this is not going to go to 0, then the idea is, okay, maybe we're not trying to obtain absolute 0. So we can try to do is, we try to minimize what? Here's a E. Here's a dispersion of E there. So what would you want then? You want the dispersion to be as small as possible, right? So then the idea is basically we want to minimize the dispersion, but this is not just one single one, right? So we create a covariance, okay, of this E here. Oop, what happened? We create what? Okay, so we create a covariance matrix here. Okay, so this is a covariance matrix, right? Yeah. We create this guy here. We call it, okay, a matrix. We call it P here. Okay, P of k plus 1. So for this matrix, it's actually going to be a diagonal matrix. Okay, so only diagonal one has elements there. All right. Yeah. Then then the idea is what? Is to basically, the objective is to minimize, okay, minimize this matrix P. So when you're minimizing this matrix P, basically we're minimizing the variance, right? Because the diagonal elements is what? It's the variance for each one of the state estimation. That makes sense, right? See, E1 of k represents the error of the first estimation, the first state, right? And E2 represents the second state estimation. So the diagonal one here is the variance of the estimation error. Okay, if you can minimize this, then you're minimizing the estimation at here. Yeah.
This thing is trying to follow a random process or stochastic process?
It is, yeah.
Is that what the balancing arm will do?
It will do, yeah, yeah. So, okay, so here's the thing, ideally there's always noise, right? But when you control the system, there are two ways you're looking at the system. Is you assume there's no noise, and you assume there is a noise. You know what I'm saying? So when you implement your controller, you implement the controller with assumption that this is a clean system. Will it work? Yes, it will. Right? And then when you implement a system, a common filter, you assume it is not a clean system with some noise in it. Right? Yeah. So it's all about how you implement the things. And it will work too. Sometimes maybe the system has too much noise, then your assumption probably won't work, right? Then you have to basically. But if the system noise is not that big, right? Yeah. So your assumption of it's a clean system is okay. Yeah. So let's say if you're doing the inverted pendulum, who's doing that one? You wanted to do that one? Or you're just thinking of it? Okay. So there are some basically disturbance inputs there, right? But if let's say the noise disturbance is actually pretty small, instead of just you're poking it, that's not random noise, right? So then your designer controller should work too. That designer controller typically basically there too is a PID to swing it up, and then you use LQR to balance it. Yeah. So it's basically the balancing part, right? And that's this equation here we're talking about here. Okay. Yeah. You linearize, basically you obtain a linear system at this operating point. Yeah. And you design an LQR basically or pole placement regulator to balance that at the vertical thing here. Okay. So the idea is to minimize this. So minimizing this one here, okay, it's equivalent, okay, when we have a cost function or performance index. So this is basically back to the similar idea as the optimal control now. So this is E times E transpose, right? And that gave us a matrix. And if you create, okay, another performance index instead of that E times E transpose, this is E transpose E. Okay, so this guy here, when that one is minimized, and this is basically become the trace, okay, of this. Okay, it's equivalent. So, all right, yeah. So you see what I'm saying here, right? When you minimize this P, you minimize all the sigma here, right? Yeah. If your performance index is this, then it basically your minimizes the total addition of all the variances. Okay? Yeah. And the other assumption that we're making is that here, okay, we call it what we have is unbiased estimation. Okay, unbiased estimation. Don't be fooled by the wording here. You actually learned this already. Okay, so let's say you have a population sample of n, okay, or 1,000 or 10,000, whatever. Okay, yeah. So now if I ask you is, okay, so this is a random variable, and then you generate 10,000 of samples. Okay. So then if I ask you is, okay, can you tell me what is the mean value of this random variable x? Let's say from random variable x. Can you tell me what's the mean value of the random variable x? So if you want to give me the exact value of the random variable x, what do? You have to mu equal to what? The expected value of x, right? That's what you get. That's the exact value. And then you had to know what? You had to know the probability distribution. Then you plug it into that integral. Then you do the integration. Then you get the mean, right? Yeah. But now if the question is, can you estimate the mean value of the random variable x based on this 10,000 samples? So what do? 1 over n sigma, like this, right? You do this. So you get an x bar, the average. So this x bar average, this guy here, it's your estimate, right? It's your estimate of the mean value or the average, right, for this random variable x. Okay, and you can prove that this one here, this is called a unbiased estimate. Okay, this is unbiased estimate. Why is this unbiased estimate? So because this basically, this means this is the one way you calculate this mean, right? Okay, so this is based on this 10,000. You do another trial, you create another 10,000, you get another x bar, right? You do another one, you get another x bar. You do maybe a million times of a trial, you get a million of this x bar here. Was that right? Then you look at basically the expected value of x bar, right? The x bar itself becomes a random variable. If you look at the expected of x bar, that basically the same as the mu, right? The mu. That's why this is called unbiased estimate. Okay, unbiased estimate. Okay, yeah. That makes sense. Basically, you're picking a certain formula, right, for the estimation. And if this formula that you picked, okay, will satisfy this condition, then it's unbiased estimate. Okay, yeah. Okay. So in our case, it's unbiased basically means what? Meaning our estimate, okay, for the x hat, right? X hat is estimate. Then the expected value of the x hat should be, what should that be? It should give me the original state variable. Okay, yeah. And one more thing, the error, okay, the mean value of the error will be 0. Okay, the mean value of error will be 0. Okay, so now let's go. Now we're ready. Let's look at it. How do I minimize this guy here? Okay, so we're talking about minimizing the p, right? How do we minimize this? And what result will generate by minimizing the capital P, this guy here? Okay, yeah. So now let's look at this one here. So we're minimizing this P here. Okay, so let's rewrite this one here. What is the E, right? E is the difference between the state variable, actual state variable, and the estimated state variable. Okay, so that's your E. Okay, that's your error. Okay, yeah. Now we do have x of k plus 1. That's your original state equation, right? What about the x hat of k? So we haven't come up with certain formula for estimating the x of k yet, right? So let's come up with a formula for estimating the x of k. So the formula we come up with is very, very similar, okay, to the Leuenberg observer that we have used, which is, okay, so x hat of k plus 1 equal to g x hat of k plus h u of k, then plus again matrix k times, okay, this y of k minus y hat of k. Okay, if you look at this one, if you think about that that observer design, look, that's just basically the same thing, right? This format. So the first two terms, we'll leave it as this, and specifically for inside this bracket here, y of k, it's cx of k plus the noise v of k. That's your actual system. Y hat is a cx hat. Okay, cx hat. Okay, that's it. That's your x hat. That's your x hat k plus 1. Alright, that's your x hat k plus 1. Yeah. So now I'm ready to basically substitute this x hat k plus 1 into this formula here, okay, into this covariance matrix. At the same time, I will substitute the x of k plus 1, basically the system's equation, this one here, okay, into that covariance matrix too. Okay, so then what do we get then? Then basically that E, okay, equal to x k plus 1 minus x hat k plus 1. So that's gonna give me, if you substitute this one, you're gonna get this one here. Okay, g minus kc x of k minus x hat of k plus w of k minus capital K and v of k. Okay, the k at here, it's this matrix, so I neglected the bracket k, so it's a changing quantity here. Okay, so it's supposed to be a changing quantity. So that's your error. Okay, that's your error. Okay, so plug this error over here and here, and you're gonna do a transpose. You're gonna expand things out. Okay, and there's a lot of things can be simplified. A lot of things will be gone, and then we'll be ready to do the minimization. Was that all right? Yeah. So I think I'll cover that in the next lecture, basically. Okay. Yeah. So next lecture, I'm not sure if I can finish all the things. Hopefully you can finish it early. If you just in case, maybe you can bring your computer here. If we finish early, then we'll start. I'll show you how to implement this using Simulink. Okay? Yeah. And then you can bring it to the experiment. Okay. So if you want, I can bring your computer. Maybe we're not able to do that, but anyways, but the next lecture will definitely be able to do that. Okay? Yeah. So just in case, bring it here.